Okay, well, welcome to the afternoon session. Our first speaker is Theo Jacobson from here, and you'll see the title.
Yeah, thanks. Let's see. Is this loud enough? Is that okay? I feel like I'll be turning a lot this way. So. Okay. Okay, so thank you for the organizers putting together this workshop. It's nice to not have to travel. So thanks also to the people who traveled a long way to be here. Yeah, I know it's a confinement workshop, but I'll be talking about Chern-Simons theory, Abelian Chern-Simons theory. So this is, of course, a deconfined theory, but I hope to say something about confinement at the end. So this is based on a recent paper with Tin. So of course, Abelian Chern-Simons theory is ubiquitous. It shows up in a lot of settings. In the study of topological order in 3 dimensions, the theory of edge modes in condensed matter physics. It shows up in, the parity anomaly, the chiral anomaly. It also plays a prevalent role in dualities, and also somewhat recently in the construction of these non-invertible symmetries in 4 dimensions. And the list goes on. But at the same time, it's a very simple theory. The action in the continuum is just A wedge dA. Maybe it's deceptively simple. And it has no non-trivial local dynamics. So this is just a theory of topological Wilson lines, which are just modeling, anyons. And naively, such a topological theory doesn't need a UV completion. So you might be wondering why do we want to put this theory on the lattice? Okay, so why discretize Chern-Simons theory? One answer is just, any quantum field theory, you want to have a setting where everything is finite and unambiguous. But especially for Chern-Simons theory, there are certain subtleties of the continuum theory that we'd like to better understand. So things like the framing anomaly, the fact that monopoles have electric charge, they're not gauge invariant, and even something like level quantization, which is a very simple thing. We want to see this on the lattice. And we're not the first people to think about Chern-Simons theory on the lattice. So there's a literature that dates back to the late 80s. But most of this literature basically ignored global aspects of the theory. And in our opinion, these are like the most interesting features. Okay, this is a theory which has no local dynamics. So the global aspects are basically all that's there. So we really want to distinguish, the fact that we're doing U1 Chern-Simons theory and not R Chern-Simons theory, for example. And in terms of applications, one obvious thing that comes to mind is in establishing exact dualities on the lattice. So particle vortex duality started off as an exact lattice duality. And then, in the years since, the late 70s, there have been many more dualities in 3 dimensions, some that relate bosonic and fermionic theories involving Chern-Simons terms. And it would be nice to try to use this formalism to establish these dualities as exact dualities on the lattice rather than infrared dualities in the continuum. And finally, it's interesting because it's not obvious that Chern-Simons theory admits a lattice regularization. And I think there might even be some lore or some belief in the community that it can't be done. So what's just one reason why this is not so trivial? One of those reasons is the need for framing. So the simplest correlation function we can look at in Chern-Simons theory is a 2-point function of Wilson loops. Okay, and it's given in terms of this Gauss formula for the linking number. But crucially, in this sum, we have to sum over I and j, and in particular, there's a term where I is equal to j, and we have to make sense of this linking number formula for this curve and itself. And that's not well defined; it's ambiguous. So we have to regularize this somehow, and this is usually done by some point splitting procedure. Okay, so we start with our contour, and we just define this sort of push off. We turn this ordinary line into some kind of ribbon, okay? And this is called framing. So obviously, depending on how one chooses to frame this line, one will compute a different self-linking number. And that self-linking number is just declared to be equal to just the ordinary linking number of like the 2 edges of this ribbon. Okay. Mustn't stop you from unrelevances. When you continue stuff, you cannot put it through, right? Without breaking. You can do it without breaking. Yeah. So if this sort of pushed off loop winds around you can't remove that by some continuous deformation, right? So yeah, that's true. And you'll just compute a different linking number. So that's just some scheme dependence. That's right. Yeah. Oh, okay, good. So there's a question of whether you can reproduce this, right? In a lattice theory where it seems like, oh, you don't have a continuous. Yeah, okay, perfect. So we'll see exactly how this comes about. Okay, so yeah, one might be wondering, how can this be reproduced on the lattice? Whether it can be reproduced, and the answer is yes. Okay, so just to set the stage in some notation, we're doing just Euclidean lattice gauge theory. Okay, and we work on a cubic or hypercubic lattice. Eventually, I'll talk about 4 dimensions. And we just take a periodic lattice. So we have sites, links, plaquettes, cubes, hypercubes, and I'll refer to fields which live on sites as 0 forms, fields which live on links are 1 forms, 2 forms, etc. And D is just the exterior derivative on the lattice. Okay, so d phi, if phi is a 0 form, that's just giving you the difference of phi on the 2 endpoints of the link. For dA, you just have this signed sum of link variables going around the plaquette and so on. Okay, so at the heart of this construction is this modified Valon formulation of abelian gauge theories. Okay. So in the usual Valon formulation, we don't use group-valued link fields, we use algebra-valued link fields, but they're supplemented by some integer-valued plaquette variables, okay, which I will sometimes call Valon variables. And in addition to the ordinary 0 form gauge invariance for this gauge field, so A going to A plus d lambda, where lambda is real, we also impose discrete 2 pi gauge redundancy. So we can shift A by an arbitrary independent 2 pi, multiple of 2 pi on each link. And this Valon variable n is just the gauge field, the discrete gauge field for those discrete shifts. Okay. So this is realizing A as a U1 gauge field where U1 is understood as R modulo 2 pi z. And just as in the continuum, we have a quantized magnetic flux. We just have to add up the values of these plaquette variables and all the plaquettes in some closed surface, and it's just manifestly an integer. And in this construction, a monopole is some field configuration where dn is non-zero for some cube on the lattice. So that indicates that there's some monopole at the center of the cube. The modified Valon formulation is just where we set all of these cube we just set dn to 0 for every cube. Okay, so we just eliminate monopoles completely from the theory. So in one way or another, this modified Valon formulation was sort of discovered either in the 90s or a few years ago. So Igor and David Gross thought about these kinds of constraints in the context of 2D theories, where they wanted a theory that had some manifest T-duality. And similarly, in these more recent constructions, these constraints really sort of give these lattice theories properties that previously only their continuum limits had. So things like their symmetries, anomalies, and dualities. Okay, so there's been lots of work using this modified Valon formulation. And when n is flat, then we can just think of n as being like a representative of the first Chern class in the continuum. So we can have a non-zero magnetic flux through some non-contractible 2-cycle. Okay, so now I'm going to start building up this lattice action. So the naive thing that we could do is we take a wedge dA and we just replace wedge by something called cup. So cup is just the lattice analog of the wedge product. Okay, so it takes a P form and a Q form and gives you a P plus Q form, and it satisfies some Leibniz rule with respect to exterior derivative. Okay, so how do we think about this cup product? Here I'm just showing an example cup product of a 1 form and a 2 form. So if you have some link on the lattice, it's naturally associated with a dual plaquette, the dual plaquette which it pierces. But we want a product between a link variable and a plaquette variable, both on the original lattice. So we just have to translate this dual plaquette shift it over to the original lattice in some direction. And so, for example, we can shift it in by half lattice unit, positive x, y, and z direction. And that gives us a product between this link and this plaquette. And then summing over the 3 directions, that gives us the cup product of a 1 form and a 2 form. Okay, so I just want to note that these cup products break lattice rotational invariance because I had to choose a particular direction with respect to which this product is defined. So if we were just doing our gauge theory, we would be done. This would just be the lattice action, but we're really after U1 compact Chern-Simons theory. Okay, and also at this stage, K is just some coupling constant, which will be fixed in a moment. Okay. So extending this to the U1 case, we need a new ingredient, which is so-called higher cup product. Okay, so unlike the wedge product in the continuum, the cup product is not graded commutative. So you take alpha cup beta, that is not equal to plus or minus beta cup alpha. Instead, you get these correction terms that involve these higher cup products. And similarly, if I took the cup 1 product of alpha and beta, that would be the cup 1 product of beta cup 1 alpha plus correction terms which involve the cup 2 product and so on. So these cup I products take a P form and a Q form and give you a P plus Q minus I form. And I think, yeah, they were first constructed in the 40s by some algebraic topologists on triangulations. But they were only given the nice sort of systematic combinatorial construction on hypercubic lattices a couple of years ago. Okay, and this is actually a physics paper. So these cup products, they're quite complicated. If you look at this paper, it reads more like a math paper, but they have a sort of simple geometric picture associated to them, and they have to do with intersections. So let's consider the sort of generic point-like intersection in 3 dimensions. That's the intersection of a line and a surface. So here I consider a line piercing a surface where both of these live on the dual lattice. Okay, and then I perform Poincare duality. So I define a 2 form, a plaquette variable, which is going to be non-zero precisely on the plaquettes which are pierced by this line. And then I define some 1 form, which is Poincare dual to this surface, so it's non-zero for all of the links which pierce that surface. And then the cup product is non-zero precisely on this cube that encircles this intersection point. Okay, so that's the interpretation of the cup product. You get higher cup products when you consider sort of non-generic intersections. So here I have a line which pierces this surface, but it goes parallel to it for some distance, and then it goes off. And precisely for the plaquettes which are pierced by these 2 lines, we find a non-vanishing cup 1 product. Okay, and similarly, we could have a non-generic intersection of 2 lines in 3 dimensions where this cup 1 product would be non-zero. And similarly, we could consider different, more complicated sort of non-generic intersections which would activate these higher cup products. So hopefully this gives you an idea of why these don't occur in the continuum, because in the continuum, we can always resolve these non-generic intersections as just ordinary intersections. Okay, so here's the lattice action. This is just the naive lattice version of A wedge dA. We have some terms involving the Valon variable, and then we have terms involving dn, which have to do with monopoles. So I'll get to those in a second. And these are just the sort of building blocks of this action. Okay, so what about level quantization? Yeah, we set the monopoles to 0 using a Lagrange multiplier. Okay, yeah, I'll get to that in a second. Yeah. Okay, so the action, okay, well, first of all, we want the action to be invariant under ordinary 0-form gauge transformations and also these discrete 1-form gauge transformations. Well, when we do this shift, the action is not quite invariant. Instead, it shifts by an integer multiple of k pi I. Okay, but that will leave the exponentiated action invariant, provided k is an even integer. So that's level quantization. If we want to do odd levels, that's really a spin TQFT. And so to do that in an intrinsically 3-dimensional way, we have to involve the spin structure in some way. Yeah. Yeah, it's an yeah. You can easily find. No, but you can easily find this is not like an even integer. You can easily find a configuration for which this is equal to 1. Yeah. So from now on, I'm just going to take k to be even. Okay, so now monopoles. So it turns out that these first 2 terms are not quite invariant under ordinary gauge transformations. They're only invariant provided dn is 0. So only in the absence of monopoles. But that's not a problem because we can just remove monopoles with a Lagrange multiplier, which implements this as a constraint. So that's what phi is. Phi is a 0 form. It lives on sites, and it just sets dn to be 0. Okay. If we want a monopole, we just have to put it in by hand. So we just insert e to the I phi at some site. That's a monopole operator. So it just tells us that now we have magnetic flux going through this 1 cube and 0 everywhere else. Okay. So I just told you that these first two terms are invariant under ordinary gauge transformations after we set dn to 0 by integrating out phi. We can also keep phi around provided we assign it an appropriate shift under gauge transformations. And that implies that the monopole operator actually picks up an electric charge. Okay, good. This term. Yeah. So this term involving cup 1 is there so that we can assign phi a local, just the usual shift under gauge transformation. If we didn't have that term, it would be sort of non-local, be split. It would be split between this side and this side. Yeah. Okay, so monopole operators have electric charge, and that's a well-known fact from continuum Chern-Simons theory that goes back to like mid-80s.
By the way, just a comment, the reason why split is the second term, which is A cup and cup A, and they don't.
Yeah, you can see this A cup 1 dn is like a little Wilson line that spreads out. Yeah. Okay, so what about framing? So it turns out that framing is tied up with a peculiar invariance of the action under these sort of staggered shifts. So the action is invariant if we shift A by some epsilon, where epsilon is staggered in this way. So this link which we shift by minus epsilon, the link which is translated in one lattice unit in each direction, we shift by plus epsilon, and then minus and plus and so on. We have this invariance under these staggered shifts. Okay, these staggered shifts are the origin of some extra zero modes on the lattice that were noticed in the older literature. But people in these older papers, they saw this as a huge flaw. They saw it as a problem. It made canonical quantization more subtle. And I think people were worried that these zero modes would somehow contaminate the correlation functions of this theory. But that turns out not to be the case at all. These zero modes actually perform an incredibly important function, and they're really crucial to the structure of the theory. And now that we've been able to connect these zero modes to a particular invariance. Yeah, we take, okay, so take an even number of lattice sites in each direction. Yeah, it loops around, yeah. Okay, so we want to view this as some kind of symmetry or some invariance. So we should ask which operators transform, or which are charged and which are neutral. Okay, so the ordinary Wilson loop transforms under the staggered shift. Okay, so we can always choose this shift such that one link in this contour gets shifted by epsilon. And then this gives us an equation, since this leaves the action invariant. We get an equation that says the Wilson loop expectation value is equal to itself times a phase, and therefore it must be identically 0. Okay, so this staggered symmetry actually projects out all of the Wilson lines, no matter how large they are. Even single plaquette Wilson loops are just identically 0. Okay. And really, this is telling us that this staggered symmetry is some kind of gauge redundancy, and it's really projecting out these operators. This was not noticed in the older literature. Static sources. Okay, maybe they have a statement like this. Yeah. Okay. But if anything, yeah, if that's true, then it was underappreciated.
They did not notice the symmetry, but they noticed that
okay.
There's something wrong.
Right. Yeah. Okay. Correlator of two Wilson loops will also vanish with this unless they are arranged in a very particular way. Okay. Okay. So what are the operators that survive this staggered symmetry? You can ask that question. Well, if you just put another copy of a Wilson loop down, insert another one, which is just translated by one lattice unit, the two phases that you accumulate will just cancel. Okay. So this configuration is neutral. And these operators are the ones that survive. So the non-trivial Wilson loop correlators, you could have a Wilson loop here and a Wilson loop here, but both of them have to be doubled. Otherwise, you'll just get 0. Okay. So this is interesting, but at long distances, these doubled Wilson loops have twice the minimal charge that you would expect. Okay. To get a minimal charge Wilson loop, we have to start with 2 charge 1/2 Wilson loops, but those are not gauge invariant, right? A fractional charge Wilson loop is not invariant under large gauge transformations. So we have to attach some surface that soaks up that large gauge transformation. So this surface is built up out of the Valon variable n. Okay, so this minimal Wilson loop is literally some kind of ribbon. Okay, so we have this little Z2 surface, which is stretched between these two charged 1/2 Wilson loops, which are separated by one lattice unit. Okay, and this is what the operator looks like. So these first two terms insert the two fractional Wilson loops, and this term with the cup 1 is what places this discrete Valon variable on that surface. And it turns out that these Wilson loops, these ribbons, are the only operators that survive the staggered symmetry. There are no other operators that are non-trivial. And moreover, they're not contaminated by the zero modes or the non-zero modes. They actually have exactly topological correlation functions. Okay, so how do we see that? So Chern-Simons theory has a ZK one-form symmetry because it's like a redundancy. It projects out. See, if W is charged under like a one-form symmetry, then only the selection rules that you get tell you that when in the limit that the contour is going to infinity, you need to get 0. Or non-contractible Wilson loops, polycup loops have to vanish. But this is saying that any size Wilson loop, even a single plaquette, is just 0. So it's like projecting out these operators completely. Okay, so we have a one-form symmetry. So we can shift A by a flat ZK valued one form. And the Wilson lines are the charged objects, but also the symmetry operators, the generators of the symmetry. So if we turn on some background field, a flat background field for this one form symmetry, which is Poincare dual to this curve on the dual lattice, that's equivalent to inserting one of these framed Wilson loops on this curve C tilde. Okay, and then the fact that this is a symmetry means we can do background gauge transformations, and those have the effect of deforming this contour. Okay, so we get this topological line operator or ribbon. Moreover, this symmetry has an 't Hooft anomaly. So the path integral is not quite invariant under background gauge transformations, but instead we will pick up some phase and some generic configuration. And that means that in a generic correlator of Wilson loops, they can be topologically deformed, but only up 2 phases. So if I consider this type of configuration where I have 2 linked Wilson loops, I can unlink them by doing this background gauge transformation, but I pick up an anomalous phase. And that anomalous phase is just the familiar linking relation for these Wilson loops in Chern-Simons theory. Okay, we can also do a slightly more subtle computation directly on the lattice, and that's of the topological spin. So now let me just consider a single Wilson loop, which is twisted in some way. Okay. I can untwist it via some background gauge transformation, and I pick up an anomalous phase. And from this anomalous phase, we can read off 2 things. One, it tells us that this line had a non-trivial self-linking, which was computed with respect to the particular framing which we chose. Okay. And 2, it tells us the topological spin of this line. So from this phase, we can read off the spin. So the spin of the charge Q anion is just Q squared over 2K. So I actually don't know of a nice continuum computation of this topological spin. Here, we're just able to do it directly on the lattice and just using these background gauge transformations. Why is it the spin? It's like, so if you had a fermionic, so physically these Wilson lines are just modeling the anyons, and putting a twist in the Wilson line is equivalent to sort of taking the anion around it. Yeah. In the continuum, you have to go through the point splitting procedure, and then, yeah, that's right. Okay, so I just wanted to comment on the connection of this Chern-Simons construction to a new form of the 4D theta term, also in this modified Valon formulation. So this first line here is just the naive sort of discretization of F wedge F in the Valon formulation. And the second line involves the monopole. And this last term, again, is a Lagrange multiplier term. So B is a one form, a real one form, and it's interpreted as the magnetic gauge field. So unlike in the continuum, on the lattice, we can have both electric and magnetic gauge fields at the same time. And due to the Witten effect, this magnetic gauge field has to transform under electric gauge transformations with the charge determined by theta. Okay, so this particular form, which makes use of this cup-1 product and so on, is slightly simpler than some existing constructions where the magnetic gauge field lives on the dual lattice and it has a sort of non-local shift. Okay, so what's the connection of this theta term to the Chern-Simons theory? Okay, so what we do is we set theta to be 2 pi times k, where k is an even integer, and we study this theory on a lattice with boundary. Okay, then almost all of these terms localize to the boundary except for this last one. This last term only localizes to the boundary provided we take this deep Higgs limit where b is pinned to, okay, b is basically exact, so it's pinned to be some d phi. And we can interpret phi as some kind of Higgs field or Stuckelberg field. And because of the Witten effect, phi carries electric charge 1, but magnetic charge k. So it's a dion. Okay, so if we set theta to be 2 pi k, where k is even, and we condense dions, then what we've done is we've actually realized some SPT phase called oblique confinement. Okay, so we condense monopoles, but those monopoles have electric charge. So this is an oblique confinement. And if we do this on a theory with boundary, we exactly reproduce this Chern-Simons theory on the boundary, where the monopole operator, e to the I phi, that phi is the same phi. It plays the role of this Stuckelberg field in the bulk. Okay. And we can couple the bulk to background fields for this one form symmetry, and we get anomaly inflow, all just directly on the lattice. Okay, so just to summarize the construction, we really just discretize U1 level K with K even on the cubic spacetime lattice, but with particular attention paid to the global structure. So we have small and large gauge invariants, we have level quantization, we have monopole operators with the correct electric charge. The observables in this theory are framed Wilson loops. They're literally ribbons. We have the one form symmetry and its drift anomaly, which we can use to compute Wilson loop correlation functions. And we have this connection to this new form of the lattice theta term. So I think there are like many worthwhile generalizations and extensions. Maybe I'll come back to this slide because I just wanted to talk a little bit about one of these, which is axion-Maxwell theory. So this is something I've been thinking about recently, and I think there's some something to say about confinement here. So what we do is we can take our theta term and just try to promote theta to a dynamical axion. So that's some 2 pi periodic scalar. So we have we want to have theta shift by an independent multiple of 2 pi at each site. And so for that, we introduce a Volan variable R, which is some integer link variable. So this axion electrodynamics is just described by that theta term, but where now theta is this dynamical axion. We have the same Lagrange multiplier, which removes monopoles. Now we can also introduce a Lagrange multiplier, which removes axion strings. So an axion string is a configuration where dr is non-zero. Okay, and then in order for everything to be gauge invariant, we also need an extra term, which involves some Chern-Simons term and couples to this Volan variable. Okay, so this Lagrange multiplier removes axion strings, but we can put them back in by just inserting some source. So inserting a Wilson surface for the C variable, that will insert an axion string. And then this term here gives us a Chern-Simons, which is flowing onto this axion string. So the axion string is two-dimensional. It's effectively some boundary of this Chern-Simons theory. And for everything to be gauge invariant, we have to add some extra degrees of freedom living on the axion string. And we can actually just do this using bosonic lattice degrees of freedom. Okay, so we can actually have some chiral bosons on the string, which couple to the gauge field and cancel the anomaly coming from this Chern-Simons term. So this is just the Callan-Harvey inflow mechanism on the lattice. Okay, so what about confinement? I think it's an interesting question to ask of whether, well, first of all, what's the phase diagram of this axion electrodynamics on the lattice? And in particular, can we make this theory confined? So if we start with pure lattice gauge theory, U1 lattice gauge theory, at strong coupling, we condense monopoles, we have electric confinement. Okay, that means we have an unbroken one-form symmetry, electric one-form symmetry, and an area law. Okay, now we couple to this axion. This axion coupling breaks the electric one-form symmetry completely. But these authors showed that actually there's some non-invertible one-form symmetry. Okay, so the group-like one-form symmetry is completely gone, but we have this non-invertible one-form symmetry. And in the continuum, this non-invertible one-form symmetry is spontaneously broken. We're just in a Coulomb phase. But now with this discretization, we can ask whether, we can force this theory into a confined phase. Okay, so now we ask at strong coupling where we condense monopoles, can we achieve confinement in this axion Maxwell theory? And if yes, that would be a phase where we have confinement, which is controlled by this non-invertible symmetry. Now, because of the Witten effect, these monopoles themselves carry some world-line degrees of freedom. So I think it's, this is something that I want to look into. I think it's a very interesting question of what does the strong coupling expansion look like in this theory, and whether we can really make it confined. And as far as I know, this is the first discretization of axion electrodynamics on the lattice. So there's no existing literature on this. Okay, so just to wrap up, generalization and extensions. We're currently working on the canonical formulation where time is continuous. It seems like it's fairly straightforward to do this for our Chern-Simons term. Here in the canonical formulation, the staggered symmetry really clearly is some gauge redundancy. So there are some extra constraints that are involved in the canonical structure. And we're hoping that this gives us also insights into lattice discretizations of chiral bosons and chiral fermions. Okay. And then finally, things that we'd like to understand better. First, the odd K theory. Again, this requires some explicit spin structure dependence. And also trying to understand the gravitational anomaly, whether we can see that on the lattice. So that's a sort of subtle aspect of the continuum theory. The framing anomaly, or the need for framing, is really just the symptom of this gravitational anomaly. It seems like it's hard to reproduce on a cubic lattice, but we can sort of repeat this construction on a triangulation, and then maybe there we can see this gravitational anomaly. Okay, so I'll stop there and take questions.
Well, I have a couple of questions. First of all, am I looking at double Wilson loops again, or can I look at a single loop?
Yeah, that's a good question. So indeed, in the absence of a Maxwell term, we should be thinking about doubled Wilson loops. So again, we'll have some kind of staggered symmetry. And yeah, that's right. Yeah, and similarly here, if we don't add here, I was imagining that we just set the gauge coupling to infinity. We just drop the Maxwell term in the bulk. But with a Maxwell term, we would have an area law for these doubled. Let me back up. Absent a Maxwell term in the bulk, also we have this staggered symmetry. And that means that ordinary Wilson loops are just strictly zero. And you can think of that as saying that you had an area law with a Maxwell term where the string tension was g squared, but then you sent g squared to infinity. So all of the Wilson loops sort of went to zero. Yeah, it's analogous to center symmetry. So it acts on Wilson loops just by the discrete phases. Yeah.
I just had a question. Does anything special happen with theta equals pi in this year?
Yeah, that's a good question. So I haven't thought about it. So in particular, I haven't thought about how this action, what's the correct sort of parity or time reversal transformation that this action would have, and then maybe that would single out theta equals pi as being special.
There is all this literature on topological insulators, right? Which has to do with theta equals pi and boundary.
Right.
I don't know if you tried to compare.
Yeah, we haven't so far. Naively, so if we really just set theta equal to pi, yeah, there will be some stuff happening on the boundary, but also some bulk dependence. Yeah, I haven't thought about it.
The confined phase, I would guess, is very similar.
Yeah.
Probably has the same.
Yeah, it probably has the same mixed anomaly. Yeah.
Okay,
It's
yeah, that's one thing I didn't mention is
Confinement,
there's.
you have to unmodify the line, like to allow.
Well, yeah, we have to somehow we have to make these monopoles dynamical. So either we can couple matter to this magnetic gauge field, and then if we condense the matter, then we'll get electric confinement. Yeah. Yeah. Yeah, it acts on the N-TOF lines in a non-invertible way. Yes. Yes. Perfect. Yeah. So we need to only condense like charge n monopoles. Yeah. Otherwise, you lose this. So the presence of this non-invertible symmetry requires at least a discrete magnetic symmetry and a discrete winding symmetry. So we just need to preserve some discrete subgroup. Yeah. Right. So the question is just about chiral fermions, how they arise in this picture. Yeah. I mean, this is a hope, but so one thing is we can study our Chern-Simons theory on a manifold with boundary, and then we find chiral bosons on the boundary. And the hope is that by studying those chiral bosons, we might gain some insights into the chiral fermion problem. Yeah. So they have a somewhat similar sort of canonical structure. Okay.
The theory with the boundary, you have to have something on the boundary to fix.
Yeah.
The theory doesn't mean very.
So either you say you interpret gauge, you set all gauge transformations on the boundary to 0, in which case you'll find some localized modes, or you allow gauge transformations on the boundary, but you have to attach either some chiral bosons or chiral fermions to soak up that anomaly.
So something option. So when you introduce monopole to it's a boundary, the
2 pi periodic. Yeah, it's 2 pi periodic when in the absence of monopoles. Yeah. Once you have monopoles, then it's really, you only have 4 pi periodicity.
Dense and complete, right? When you set
no, so this only happens when k is even. So if k is odd, then you actually will still have some bulk dependence. Yeah, 4 pi periodic. Yeah. Yeah, yeah.
This is, I think, like targeted but everything
Yeah, so actually I was a little bit quick. In this axion Maxwell theory, I imagine that I introduce also some coupling, some discrete coupling k, which is an even integer, so that I have 2 pi periodicity of the axion.
I still on this problem might be missing, problems to comment about continuity, right? Because in this way, people speak on the latest, the notion of topology is lost. I mean,
Well,
you can jump.
No, but I think if we look at this picture, the 2 ends of this ribbon are clearly linked. I mean, that's some topology that's on the lattice. Right?
Yeah, but it's like a kink between these two spaces or whatever. You see, you can introduce a huge jump at the distance, which is also more continuity. Right? So someone should in your approach should evaluate that it's kind of doesn't changes the size of the lattice size.
So maybe one answer is that in this Valon formulation, the topology is sort of put in by having these discrete fields. Okay, and absent those discrete fields, so Yuya is going to talk about how this works absent the discrete fields in his talk later this week. So how do you put the topology back in the lattice? Yeah.
Okay, so I think so. So since you import the monopole response frame to target that particular yeah, so correspondence. But also you have data on the links which are gauge fields, and then you supplement them with some data on stochastic, which shows you the flux, the integer of the flux to the stochastic. And then when you move these things, as we move both of them, you can still preserve some.
Yeah, but you're not allowing to want to go into the gap, right? Because you're still there. Like it's size, right? But there is you can say, the case will go through.
But it's sufficient to, I think, capture everything.
It's suppose you take just compact QED in 3 dimensions, not Chern-Simons, and put in this zero monopole constraint. Does that make the theory completely trivial, or?
So it's I mean, it's
it's
you lose the linear potential. You just have
So
some
it
log.
becomes free, or?
Yeah, so you can dualize that theory to
That's
a
what
compact
it sounds
scalar.
like.
Yeah, yeah,
That-
maybe.
one of-
But yeah, so you can dualize that theory to a compact scalar where now you have a no vortex constraint.
I think they did look at this type of model.
Yeah, yeah.
What about non-abelian? Can you use the?
Yeah. For that, no, and I don't know how to do it using this Valon approach. So I think Yuya is going to talk about how to define topological charge in SUN theories. Yeah, for Chern-Simons it's a little more difficult. I mean, something we have U1 level 2, and there's a level rank duality with SU2 level 1. So if you believe the level rank duality, which really there are some subtleties there, then we can do that one non-abelian case. But I think it would be very satisfying to have a non-abelian construction where you could also verify level rank dualities on the lattice. Yeah, okay. So there are some things you can do where you have multiple U1 factors, and then you gauge like a permutation symmetry, discrete permutation symmetry, and you can get some non-abelian Chern-Simons that way. But those are discrete. I think those are discrete non-abelian Chern-Simons here, yeah, or finite group.
Okay, well, if there are no more questions, let's thank you again.